Is a presentation for shift registers, typically made of D latches, and they're a register for holding a temporary data. So when we clock it, we take that input from the data line and we move it to the queue. Okay, and as a 0 goes in, it goes out as a 0 once we clock it. So depending on how we connect these things, we could have a storage of zeros and ones, and we could move them from place to place. Here we're showing serial data movement in registers. These are known as SISO, S-I-S-O, serial shift in and serial shift out. Here we have a serial shift right then out, where all the digits come in and then out. Rotate right is where we capture the digits and we continually rotate them among the bits that we have. Serial shift left then out, we have data coming in and eventually coming out. And where we trap it, rotate left, where we rotate around and capture the digits and continuously rotate them. Here we're showing parallel data movement in registers. This is PIPO, parallel in, parallel out. And we show the digits coming in and then coming out, and they're coming in and out in parallel. Here we're showing the serial in, serial out, SISO, S-I-S-O, where we show the emptiness and then we load a number and we continue to move those bits over until they eventually come out. So this would be serial in, serial out. Here we're showing another parallel in and parallel out shift register. We're going to load them through A, B, and C, and we're going to come out of queues. And if you notice here, this is a more realistic. This is based on, we have a shift and load and a clear and then our clock. So these would be typical inputs of a standard shift register. Here's a common shift register known as a Johnson counter. It's a standard one. It's on the FCC exam, and it's a standard counter where we take all the data and we shift it across, and we take the Q bar and we feed it back into D. So we're constantly rotating these 4 bits. So depending on how we load these, we're going to go 4 up and 4 down continuously. So we're recycling these continuously. This is a Johnson counter where we have 4 up, 4 down, or the number of bits up and down. Here's a standard counter too, known as a ring counter, and the difference between this and a Johnson is we feed Q back. So once we load the data in, that constant data will just trip apart across and then repeat. Here we've loaded a 1 1 and then we're shifting that data apart. So ring counters come out of Q, Johnson counters come out of Q naught. Here's another ring counter, and this time what we did is we loaded 1 1 1. So we got 3 bits right next to each other, and you can see a ring counter just shifts them over one at a time, the same pattern. Here's a standard shift register as an IC. We no longer do these because they're kind of complicated and they're obsolete. We will do shift registers when we do the microcontrollers. But this is a standard one, and this is an 8-bit serial in, parallel out. So this is a SIPO, serial in, parallel out, S-I-P-O. Here is another shift register, the 74165. It is an 8-bit parallel in or serial in and serial out. So this one could be used as a PIPO, parallel in, serial out, or excuse me, a PISO, parallel in, serial out, P-I-S-O, or serial in, serial out, a SISO, serial in, serial out, S-I-S-O. This would be a good candidate to do serial communication, let's say RS-232 in a computer, where we could take an 8-bit parallel in from the microprocessor and we could go out serially like we would do on a serial communication. And we could run it the other way, where we have serial in and then have a serial output. Here's another example of a shift register, 74166. 8-bit parallel in and serial out, or a 8-bit serial in and serial output. Here are some examples of shift registers used in the 8085 Intel microprocessor. These are used to move data and to condition data. So we have a carry flag and we have an 8-bit register called the accumulator. Okay, so we have RAR, rotate all right. So our digits are going to move over to the right, starting from our carry flag, and they're going to move over, and then they're going to refill the carry flag. We have RRC, which I call rotate right and carry. So we're going to move the same 8-bit digits around continuously, and we're going to put the digit back into the carry flag. Here's RAL, rotate all left, where we're going to continuously move left and utilize the carry flag. So we have 9 digits moving. Then we have RLC, rotate left with carry, and we're going to rotate those 8 bits within that register, and then we're going to put one of them in the carry flag.